Greetings, welcome to lecture number 32 on basic circuit theory. I am Razavi. Today we will continue to look at the lossy parallel RLC circuit and finish up its analysis in the case of an input applied to the circuit. So we will consider all these three cases, the overdamped and critically damped and underdamped responses according to the situations that we have discovered before. All right, but before we go there, let's take a look at what we learned about the circuit last time when the input is a current step. So it jumps from 0 to I1 at time 0, and we don't have any initial conditions here. So we decided that this current flows into this node, and now it has to figure out which one of these branches it wants to flow through. So we decided that at time 0 plus, the capacitor wants to maintain a 0 volt difference here, so it doesn't allow any current to flow through R1 because R1 has 0 volts across it. And the inductor doesn't want to have any current, so all of the current has to flow through C1. At time infinity, on the other hand, because all of the quantities have reached constant values, the voltage on the capacitor is constant, the current through the capacitor is 0. And the voltage across the inductor is 0, so all of the current flows through the inductor and not through the resistor. So then we wrote the differential equation governing the circuit, and this differential equation was given by this current equal to this current plus this current plus this current. And what we saw was that actually this should be the derivative of di in over dt. We ended up with this differential equation. All right, now if we consider the simple case of I in as a step, then this derivative would be equal to I1 and impulse of t, delta t. So qualitatively speaking, we saw that for the case of overdamped response, you would expect something along the lines for these four quantities. So the input current jumps from 0 to I1 at time 0. That's the step. Then we have V out, which starts from 0 and doesn't jump because the capacitor wants to hold this voltage at 0 plus. But then it gradually goes up and it comes back to 0. We know it has to be 0 at time infinity because this inductor creates a short. We know it has to be 0 at 0 plus because this capacitor creates a short. And in between, it will be reach some maximum value. Then we saw that the inductor current starts from 0, as 0 plus is still 0. But at time infinity, all of this current flows through the inductor. So the inductor current should go from 0 to I1. And finally, the most interesting part was the current through the capacitor. And we saw the current through the capacitor jumps to I1 at time 0 plus. All the current flows this way. And as time goes by, the current goes towards 0. But we decided that for this plot to be consistent with c dv over dt, actually, we have to go to negative values because the derivative here goes to 0 and then to negative values. And then we come back to 0. So, so this qualitative behavior tells us that we can represent V out by two exponentials, and then we have to figure out how we're going to represent these two currents. So let's go to where we stopped last time and see what we should do here. So we said that, so here's our driven parallel RLC circuit. So I have to draw that again. So we have a current source attached to a cap C1, an inductor L1, a resistor R1, and we are interested in this voltage for now. Okay, and this is I1 U of t. So we consider the case of overdamped response. So we say case 1, overdamped, and that means that given that the characteristic equation doesn't change, whether we have an input or we don't have an input, the roots of the polynomial are still the same. So S12 is minus 1 over 2R1C1 plus minus, I always forget this factor of 1/2 here, 1 over R1 squared C1 squared minus 4 over L1 C1. Okay? And the overdamped response means that this term under the square root is positive, which corresponds to R1 being small enough. So 1/2 of square root of L1 over C1. Okay, so last time we said that the output voltage can be expressed as A1 e to the S1t plus A2 e to the S2t. And then we found how A1 and A2 came about, right? We said that we have to enforce two initial conditions. So A1 plus A2 is 0, because that's V out at 0 plus, which is 0. And then the other condition came from the current of the inductor being 0. We saw that times 0 plus, all of this current flows through C1, right? Not through R, because the voltage is 0 still. The capacitor wants to keep the voltage 0. So for the other condition, we wrote a C1 dV out over dt at 0 plus is equal to I1. All the current flows through C1. So we have to take the derivative of this, evaluate at time 0, and equate the result to I1 over C1. So we have A1 S1, e to the S1 times 0 goes to 0, plus A2 S2. The derivative at time 0 plus should be I1 over C1. So I1 over C1. So with these two equations, we can obtain A1 and A2. Okay, so that's great. And that seems to predict our responses that we just saw. So let's pull this over here without overlapping the board too much, and you can see. Okay, so I have managed to solve this equation by predicting that V out is of the exponential form, and that's what we got for V out. Now there is something that's probably bothering you, and that's the fact that there's an impulse on this side, right? I don't have an impulse in this waveform. Does it make sense? So how can I have an impulse on this side, but V out itself does not have an impulse, right? Okay, so we have to see when we plug in this V out expression into this equation, do we satisfy both sides? This side has to be I1 delta of t. This side has V out, its derivative, its second derivative, all that. When we plug them in here, do these two sides become equal or not? If they don't become equal, we have a problem. So what we know is that, okay, V out doesn't seem to have an impulse, but the first and second derivatives may. Why? Well, this is because actually V out is not just this, right? So V out, to be precise, is the following. This is multiplied by U of t, right? Because we see that V out is 0 before time 0, and then it assumes this form. V out is not any of these exponentials before time 0, right? So it has to be multiplied by U of t. So now that we have the complete shape of V out, according to this equation, we can go ahead and plug it in this equation and see if it satisfies this side being equal to I1 delta of t. So let's go ahead and do that just to make sure that we are not missing anything. I have claimed that V out itself can be just like before, like our natural response, but I have to make sure that that's actually true when I plug it in here. Okay, so we're going to verify. So we say verify the differential equation. And what that means is that we have to take V out and divide by L1. And then we have to take the derivative, divide by R1. Then we have to take the second derivative, multiply by C1. And these all have to add up to I1 delta T. So let's see how that goes. Okay, so let's go ahead and find dV out over dt. So that's just the derivative here. We have the derivative of this part times u of t, then derivative of this part times this. So we have a1 s1 e to the s1t plus a2 s2 e to the s2t times u of t. So far so good. And then we have the derivative of this, delta of t, times this. So we have a1 e to the s1t plus a2 e to the s2t. I have to push this board farther away, times delta of t. So that is the derivative of V out, right? Okay, now we can make some simplification. We know that a function multiplied by delta of t is equal to the function evaluated at time 0 multiplied by delta of t. Remember we called this the sampling or sifting property of the impulse. So we evaluate this at time 0. That is the weight or the area of this impulse. How much is this at time 0? Well, we know that because this is V out itself, right? At time 0 plus, it is 0. Remember that the output voltage is 0 right here before it takes off? So indeed, this whole thing, this has an area of 0, so this whole thing goes away. Because we have an impulse with an area of 0, so that impulse doesn't exist. Okay, so the derivative of V out still doesn't have an impulse in it. Does it mean we're in trouble because we still need an impulse, right? Well, no. Let's go to the second derivative. So now we go to the second derivative. And that's again derivative of this times this and the other way around. So we have a1 s1 squared e to the s1t plus a2 s2 squared e to the s2t times u of t. And then we have the derivative of this times this. So plus a1 e to the a1 s1 e to the s1t plus a2 s2 e to the s2t times u of times delta of t, because I'm taking the derivative of the step. So derivative of this times that. All right, so far so good. Okay, so what can I say about this? This is the part that's fine. This the other parts that have u of t will add up to 0. Why? Because they add up to the characteristic equation of the circuit, so they should add up to 0. Right? If you multiply this by C1, multiply this by 1 over R1, multiply this by 1 over L1, add them up. All these parts that have u of t add up to 0, so that's fine. We just have to worry about the impulse part of it and see if that is consistent. Okay, so this equation says that multiply the second derivative by C1. So this is multiplied by C1, this is multiplied by C1. So for the left side of this equation, to agree with the right side, what we would expect is that if I multiply this by C1, it should come out to be I1. I1, I guess you should be able to see it in the equation, is I1, right? So if I multiply the coefficient of delta on the left side by C1, I should get this I1 on the right-hand side. So, in other words, what I'm looking for is this. Can I say that C1 times A1 S1 e to the S1t plus A2 S2 e to the S2t times delta of t is equal to I1 delta of t. I have to verify this, right? If I verify this, then I'm all set. I know everything is consistent. This is the right side of the differential equation. This is the left side of the differential equation. Is that true? Well, yes. So first of all, because this is multiplied by delta of t, we just need to evaluate this at time 0, right? This is the weight of the impulse. So that means that this is just equal to C1 A1 S1 plus A2 S2 times delta of t. So in other words, what I need to check is the following. So let's go back to this color. I need to check to see if this whole thing is equal to I1. I put a question mark here, right? I need to make sure that this is I1, then we have consistency between two sides. Okay, so how do we do that? Well, we have to go back to these equations actually. So this equation says that A1 is equal to minus A2. And if I plug this in here, this equation says that A1 times S1 minus S2, because A2 is minus A1, right, is equal to I1 over C1. All right? So if so that means that I can put that here. So you can see now that this will be equal to C1. A1 S1 plus A2 S2 is given by this expression here. So actually I don't even need this, right? So A1 S1 plus A2 S2 is I1 over C1, right? So I1 over C1. And we can see that this is indeed delta of t. And indeed, this is just I1 delta of t. Okay? So actually, you don't have to worry about this part. So don't worry. We're going to need this a little later. So I got ahead of myself. So don't worry about this for now. You can keep that. Okay, so what we see is that A1 S1 plus A2 S2 is equal to I1 C over C1. So C1 cancels, and indeed, this is just I1 delta of t. So everything checks out. The fact that our voltage was assumed to have this shape only, without any impulses in it or anything else, is fine. We can see that it actually verifies the differential equation. Okay, so that's of course all for overdamped response, but that's okay as we go along. For other responses, the behavior is similar. All right, so with that, now we can go ahead and look at a few more quantities in the circuit which are interesting. So one quantity that I want to look at is the current through the capacitors. So let's try to find that. So we say I cap. Remember the waveform that we had for the capacitor current? It looks like this, right? The capacitor current, I think you can see it, maybe not. We should raise this a little bit. So the capacitor current looks like this. It goes down, dips below 0, and then comes back. So we want to see how we can derive the equation for the capacitor current given what we have obtained so far. All right, not a problem. We know that the capacitor current is just C1 dV out over dt because it's the same voltage. And we have V out, so we can just go ahead and take the derivative of V out, right? So we say is equal to C1, then the derivative of this whole thing, which we tried before, right, was right here. And this is 0. So it's just A1 S1 e to the S1t plus A2 S2 e to the S2t, and then times u of t. Okay, very simple. So this equation is for the plot of capacitor current that we saw before. All right, So that's fine. Now the next quantity that's interesting to find is the current through the inductor. So this is a little tricky, and we just have to patiently and carefully see what we can do here. All right, so the current of the inductor is equal to 1 over the inductor value, integral of the voltage across it. All right, so that seems easy enough. I can just go ahead and integrate this function and call it the current of my inductor divided by L1. All right, so let's go ahead and do that. So we're going to write 1 over L1 and then integral of this function. So A1 over S1 e to the S1t plus A2 over S2 e to the S2t, and then U of t. U of t still remains, right? Because remember that the current through the inductor was 0 before time 0, so it still gets multiplied by U of t. Well, but something is missing here. It's not quite correct, right? The way I can tell is the following. The current waveform that we had here for the inductor was like this. I'll try to lift this so you can see it. The current to the inductor was 0 and then approached I1 at time infinity, right? Does this do the same thing? Not really, right? Because you can see that if the time goes to infinity, this goes to 0, this goes to 0, the whole thing goes to 0. So we have a problem. This equation is not correct. So what are we doing wrong anyway? Didn't we just integrate the voltage and divide by L? So what's wrong? Well, remember, every time you integrate, you have to worry about the integration constant. That's not always 0, right? So we do have to put an integration constant here. Let's call it K or something, right? And we have to figure out how much K is. So how do we figure this out? Okay, well, the way we approach this is that we say we want to make sure that the current, this current at time 0 plus is equal to 0. We know that, right? The current to the inductor at time 0 plus is 0. So to find the integration constant, we enforce that condition. So we say inductor current equals 0 at 0 plus. So we go ahead and plug in 0 plus there. That says that 1 over L1, A1 over S1 plus A2 over S2 plus K. U of t is 1 at time 0 plus, right? Plus K must be 0. Okay, so that gives us the value of K. So K is this much, is minus 1 over L1, A1 over S1 plus A2 over S2. So that goes in here, and this completes the response as far as the current through the inductor is concerned. All right, so, but something is missing here. We said that the current through this inductor at time infinity is this current, right? All of it goes in there. We saw that in our plot, the current through the inductor started from 0 and went up to I1, right? That's what we saw before. But do you see I1 in this equation that I obtained? There doesn't seem to be any I1. Where is I1? So there's no I1 here, and K is this. At time infinity, this is 0, so this had better be I1, right? Otherwise, we have a problem. So what we are hoping is that this quantity is equal to I1. So we have to verify that. Fortunately, it is, as expected, right? So what happens actually, I'm going to go back here. We play with these, because these are always true, right? So A1 plus A2 gives 0, so A1 is equal to minus A2. And similarly here, I can say that A1 times Because A2 and A1 are opposite of each other, I factor and I get S1 minus S2 is equal to I1 over C1. Okay? So we go back here, and again, remember that A2 is equal to minus A1. So we say K is equal to minus 1 over L1, then A1 over S1 minus A1 over S2, right? And then I can factor A1 out. So A1 with a negative sign over L1 times S1, S2, and then S2 minus S1. So we're almost there. We just need to work a little more to prove that this whole quantity is equal to I1. Okay, so what we see is that A1 times S1 minus S2 is I1 over C1. So what I can say is that this part is equal to I1 over C1. Okay? The whole thing has to be equal to I1, but I have found that that numerator part is I1 over C1. So then what else can I do? Well, you got to remember S1 and S2. S1 is this with the negative sign, S2 is with the positive sign. You have to multiply these two. It becomes this squared minus this squared. Subtract, simplify, and indeed you will see that this is equal to I1. So I'll leave that as an exercise for you. S1, S2. So they take S1 and S2, multiply them by each other. It will simplify. Certain things will cancel, and the rest will also cancel with this L1 and that C1, so you end up with I1. Okay, so that's good. All right, so we have found the voltage across the whole circuit. We have found that this current as a function of time, is that equation on top of the page. This equation for the inductor, which is this plus this, or actually plus I1, it's the same thing. And the equation for R1 is similar, right? The current through R1 is how much? It's just V out over R1, so just this divided by R1, that's the current. So we have found every unknown about the circuit in the case of overdamped response. Okay, so we can now go ahead and look at other types of response. Let's see if there's anything else that I want to mention here. Okay, so let's go to case number 2. We say critically damped response. Okay, so that happens when R1 is equal to this value. So this goes to 0. The two roots are equal. And remember that that's the situation that we have to keep in mind. So we say the out is equal to A1 e to the S1t plus A2 t e to the S1t. S1 is just this value because it is 0. All right, very good. Does this take a u of t? Yes, it does, right? Because before time 0, the output is 0. Okay, so we have that. And we just need to find A1 and A2. And again, same story. We have to enforce this condition at time 0. And then we have to enforce this condition for the current that flows through this whole thing. So that this current has to end up in the capacitor, not in the inductor or the resistor at time 0 plus. And that doesn't depend on the type of response. Whether we have this or this or this is always true. Okay, so then we say at time 0 plus, this is 0. We have only A1, so A1 is equal to 0 because the output voltage at time 0 plus is 0. And then you also have to enforce this condition, meaning that the derivative, this condition here, the derivative at time 0 plus is given by I1 over C1. So derivative of this guy has to be obtained. So that would be A1 S1 plus derivative of this 1 times that, so A2. That has to be equal to I1 over C1. Is that confusing? Well, so The derivative of V out is the derivative of this times U of t, which comes out to be this, plus the derivative of this times this. The derivative of this would be delta of t times that. How much is this evaluated at time 0? 0 plus. It is 0, right? We just decided it was 0 because that was the output voltage. So when you find delta of t times this, the area of that impulse, the weight of that impulse is 0, so that's why it doesn't enter the equation here. Okay, so again, we can find A1. A1 is 0, and A2 comes out from this equation. So it's a very simple response. So actually, it's interesting in this case because we have only A2, so we see that A2 is equal to I1 over C1. So we have only this exponential multiplied by a ramp, right? It's just that, and it goes and falls down as we saw before. So when we have a critically damped response, V out is similar, except that it settles as fast as possible here. If you make the resistor any larger, then V out will try to go below 0 before it comes back. But as long as the resistor is this value or smaller, V out just settles like this without going under 0, below 0 and coming back, without any undershoot. Okay. All right, so that is the situation of critically damped response. And once we have V out, of course, we can find everything else, right? We follow the same procedure for the current through the capacitor and the current through the inductor. Okay, and then finally, we consider the underdamped response. So underdamped response. So in this case, what we have is that R1 is greater than this value, so the roots become complex. So R1 is greater than 1/2 of L1 over C1. And we decided that that gives us this type of response. So again, we write V out is equal to, we have a step, so I'm going to put these in parentheses, A1 e to the alpha t cosine of omega 1t plus A2 e to the alpha t sine of omega 1t times u of t. And remember that alpha is this value here. So alpha is minus 1 over 2R1C1. And omega 1 is this value, except that these are swapped. So omega 1 is equal to 1/2 of 4 over L1C1 minus 1 over R1 squared C1 squared. Okay. All right, I should mention that some textbooks prefer to call 1 over 2R1C1 alpha, okay, without the negative sign, and then they put a negative sign here. That's possible too. I prefer to do it this way because it's simpler, but some textbooks put the negative sign over here. So that should not be confusing because they assume alpha is just 1 over 2R1C1, not minus 1 over 2R1C1. Okay, so in this case, what we expect is that the response has some ups and downs. This is what we call ringing. The output rings before it settles. So, for example, for V out itself, what we expect to see as a function of time is that it starts from 0, right? We know that should happen. And it goes up, but then it comes down and it does something like this before it settles to 0. Okay, so it has this oscillatory behavior depending on how underdamped the response is. The larger this resistor is, the more underdamped the situation is, right? If R1 goes to infinity, if it's out of the picture, of course, this will just go like this forever, right? It will oscillate forever. Okay, so that's the case of underdamped response. To find A1 and A2, we follow the same procedure. we say V out at 0 plus must be 0. So at 0 plus, you can see that this A1 is here. This is 0. So we say A1 is equal to 0. A1, yes, A1 is equal to 0 because we have the whole V out at 0 plus must be 0. And when I plug in t equals 0, this goes away anyway, so A1 has to be 0. And then we also have to satisfy this condition. This condition tells us that the derivative of V out at time 0 must be equal to I1 over C1. So we have to take the derivative of this. I'll leave that as an exercise for you. So we say dV out over dt at 0 plus must be also equal to I1 over C1. So from this equation, we can find A2. In this case, actually, it's a little simpler because if A1 is 0 anyway, so we don't have to worry about this. We just take the derivative of this guy at time 0 plus. Take the derivative, replace t with 0 plus, and calculate that, equate it to I1 over C1. That gives us the value of A2. Okay, so this is the response of the circuit in these three cases. The key point here is that in response to a step of current at the input, V out wants to start from 0, go up and then come back to 0. Now, whether it just goes up and comes down monotonically or it does this depends on the value of R1 with respect to this threshold, right? And if R1 is small enough, it doesn't have this type of ringing effect. If it's not small enough, then yes, it will. All right, so let's see. Anything else that I wanted to add here? Okay. All right, so another type of response that we can think about for this driven circuit is when the input is an impulse, not a pulse, not a step. So instead of I1, instead of the current jumping from 0 to I1 and staying at I1, we can assume that the input is an impulse. So it's at 0, then jumps to infinity and comes back, and it has a certain area under it, certain weight associated with it, and we would like to see what the circuit does when we give it that impulse. So let's analyze that one too, and then we're done with the circuit because we have examined it from so many different perspectives. Okay, so let's go to the next page and see what we can do about the impulse response. Okay, so we say impulse response. All right, so same situation as before. I have an impulse here, so I'm going to call this maybe, let's see, I'll call it A delta of t. And then we have our capacitor, inductor, resistor combination, C1, L1, R1. And we are interested in this voltage. And of course, all the currents. So once we have one quantity, it's not that hard to find the other quantities. Okay. All right, so what's happening is that this current source arrives like this as a function of time. Right? At time 0, we have this impulse with an area of A, little a, and this impulse comes to the circuit as a current. It's a current that is very, very short in time, very, very tall in amplitude, and it injects a certain amount of charge into the circuit, and then it goes away. Right? So before this point, we have no current. It's an open circuit. After this point, we have no current. It's an open circuit. At this point in time, we just give some charge to the circuit. And the question is, where does the charge go? And then how does the circuit respond? All right? Okay. So, well, it shouldn't be that hard. We figure that we have this inductor dictating certain conditions, this capacitor dictating certain conditions, and this resistor dictating some conditions. So from all of these, we should be able to figure out where the charge associated with this impulse of current goes, right? Okay, so let's ask, can this current flow through this resistor? No. Why? Because if the current flows through R1, the voltage across R1 will jump to infinity. And that's definitely not possible. Why? Because the voltage on the capacitor doesn't want to jump to infinity, right? The voltage on the capacitor can jump by a finite amount if we have infinite current available, which is the case here. But the voltage on the capacitor cannot jump to infinity, right? It can just jump by some amount. So the voltage across the resistor cannot jump to infinity, which means this impulse cannot flow through this resistor. All right. Can this impulse of current flow through the inductor? No, because the inductor says, I would like to satisfy this condition, right? So dIL over dt. So if the impulse of current goes through this, we have the derivative of the impulse as the voltage. And that's not possible. The derivative of impulse, you might know, is called the doublet. It's a little complicated, but in any case, that's not possible because this V out is still governed by C1. So what really happens is that the current provided by that impulse has to go to C1 only. It cannot go anywhere else. That's the only condition where all the equations for the resistor and the capacitor and the inductor come out to be consistent. So now for the capacitor, we say, for example, I capacitor is equal to C1 dV out over dt. Or we can say V cap or V out is equal to 1 over C1 integral of I cap dt. So here's what happens. If you monitor V out, this is what's happening. V out as a function of time, which is the same as across the capacitor, does this. It's 0. At time 0, it jumps. Why does it jump? Because we managed to create an impulse of current that went through the capacitor. We had infinite current available for the capacitor, so the capacitor voltage jumped. And we can calculate how much that jump is, right? From this equation. We can say it's 1 over C1 integral of A delta of t dt. Integral of an impulse is 1, so this is just A over C. So the height here is A over C. So we see that the capacitor voltage jumped by some amount. All the current carried by the impulse went through the capacitor. All right? So what we know also is that the current through the inductor, for example, so let's call this I inductor, is 0. And it will probably want to go up, and it should, and we don't know exactly what happens and so on, but at time 0 plus, it's still 0. Okay? If the current through the inductor wanted to jump, it would require an infinite voltage available. But we don't have an infinite voltage available. Why? Because the capacitor cannot deliver infinite voltage. For a capacitor to deliver infinite voltage, the derivative of the current has to be infinite. But the derivative of current cannot be infinite because the current itself is an impulse. Right? So in any case, that's what we get. Okay, so we have this situation, and now that we look at the circuit after 0 plus, we see something interesting, right? At the 0 plus, we see that the circuit has some voltage on the capacitor, right? Some charge on the capacitor, no current in the inductor, and this circuit actually looks like the undriven RLC circuit we studied before. Remember, we had the same circuit with an initial condition? This is the same thing. In other words, whether I have an impulse of current and no initial conditions, or whether I have no input and an initial condition across the capacitor, the circuit is the same. In fact, theoretically, to generate an initial condition on a capacitor, I can just give it an impulse of current, and that's how I generate the voltage across the capacitor. So this circuit is indistinguishable from the original circuit we studied with no input and an initial voltage on the capacitor. These two are exactly the same, and of course the response will be exactly the same. So what will happen is that from here on, V out actually doesn't do this, right? V out goes like this, as we saw before. And then I inductor goes down like this, and so on, just the way we studied before. So the key is that the impulse response of the circuit is similar to when we had only an initial condition across the capacitor. I will see you next time.